For example, I might be in a O basis, right? The O1, right? The O1 might have the vector like let's call it the basis vector might be, let's call it IO, right? So it has n of them, n-dimensional. Understand what you mean? Right? You have the basis vector, which is the IO from 0 to n minus 1, right? And then we go to the new basis. I call it the I new. Right? So how do you transform a vector from an old basis to the new basis? Remember? You construct the matrix. How do you construct the matrix? Is it eigenvalue? Remember the matrix? We construct a matrix. So if I vector, let's say my vector is the psi in the old basis, to transform to the new basis representation, we use a matrix, right? So that new equals to m times psi O, right? Remember this one? You just done assignment 1. How do you construct m? M equals to what? No one remember?
The eigenvector projected with the.
So I think in order to let me enable me write it easier, right? Instead of using this new and O, I just call it dash. Dash is the new, right? Remember? What do you get? 0 dash 0, 0 dash 1, 0 dash n minus 1. Do you remember this matrix? I may be wrong. I don't have it on my cheat sheet, but I think that is right. I just check it carefully when you go back. It's very easy to memorize because the inner product, the bra is the new one, and the new is the row, the old one is the column. So that's how I memorize it. Right? The last one is n minus 1 dash 0 all the way to n minus 1 dash n minus 1. Is this okay? Right? For example, my old basis may be the basis of the 0, 1 basis. The new basis may be the basis of the plus minus basis. It's good to keep reminding ourselves what we are talking about. For example, this one can be 0, 1. This one can be plus, minus. What is n in this case? N is 2. It's two-dimensional, right? This is just an example, right? Any questions? So we know how to transform a vector in the old basis representation to the new basis, right? But how about a matrix? If I have a matrix, what do we do? Then that is the question of this slide, right? So we assume there's an operation right? I call it U. Okay? What it does is this. It do the rotation of a vector to another vector, right? Quantum computing is nothing but the rotation of a vector in its hyperspace, right? So this can be a quantum gate, U. Is that okay? I just say, assume I have an operator which does this. Do you understand what you mean? I have a vector psi, apply an operation, which is a matrix, then it becomes another vector phi. Okay? Now, of course, in the O basis, probably I can write it as this. Right? The O basis representation of all the vector and the operator. Okay? Then in the new basis, I'm just rotating a vector. How do I represent it has nothing to do. The vector still rotate, right? It's still the same. The physics is still the same, but just the representation is different. For example, I put my pen on the table, I move it up by 1 meter, that is a transformation. Maybe let me do rotation. I put my pen like this vertically up, then I rotate it 45 degrees. Then you can say it is vertically up and I'm rotating by 45 degrees, right? But I can change the coordinate. I can look at it by 90 degrees, then I can say actually it is horizontal because for me now it's horizontal, right? And then it is still rotating, right? And then I can say it's rotating up by 45 degrees. The physics is still the same, right? So my question is, in the new basis, of course, I would have my representation of the same vector in the new basis. I also have the representing of the same rotator vector, right? This is the rotator vector. So phi is the rotator one. And there must be the matrix is still there. The matrix should still be there, right? Isn't that? Because this is the same operation. I'm just looking it at different coordinates, different bases, right? So the question here is, I know how to relate the O to nu. I already know that. I know. Psi nu equals to M psi O, right? Am I right? How about this phi nu equals to what? Also M phi O, right? Because they're vector. My question is, what is the relationship between U nu and UO? This is the question we are asking. Okay?
So that M is the same for both psi and...
It should be the same because it's just a vector. The M represents the transformation from one basis to another basis. Then all the vector inside the basis should be related to the corresponding vector in the other basis by the same matrix, right? And you see that this matrix only depends on the relationship of the basis vector, not depending on which vector you are talking about, right? This is the transformation matrix, right? Is this okay? So it's not too difficult. Then let's just draw a diagram, then you'll be easy to see. So I have my O, the original vector before the rotation in the O basis, right? And then I know what? I apply the representation in the O basis to do a transformation. It becomes the new vector, but still in the O basis, right? Which is equals to UO psi O. Is this okay? Just restating what I'm doing here, right? UO psi O equal to phi O. In the O basis, right? Just like I'm standing still, I rotate the pen. That is what happened, right? At the same time, I know that if I do this transformation, I can represent it in the new basis for the same initial vector. And then if I apply this new, assume I know that, then I will get the new phi, which is equal to the new u times phi new, right? This again, I'm just repeating this statement. In the new coordinate, I rotate the initial vector by this u operator, I get phi new. Okay? But of course, I also know that this one is related by m, right? The O, even the rotator one in the O coordinate is related to the rotator one in the new coordinate by m, right? Where psi, not psi, phi new equals to m times phi O. Right, so I'm just repeating what I said. I have not introduced anything new yet. Okay? Now, because of this, then we can do some substitution here. Let me use another color. What is phi new? We already know phi new is equals to, as I show here, equals to u new times psi new. Okay? I'm just saying that this is phi new, right? Phi new equal to u new times psi new. And we also have m. I just copy m. M is here. And then what is phi O? Phi O, I already know that it is uO times psi O, right? Okay, I just do substitution. Again, I know that phi new equal to phi O times m because they're different coordinates. And then I just substitute this one. This is u new times phi new, right? And this is the uO times phi O, psi O, sorry, I keep saying that psi O equal to phi O, right? Then what I'm going to do is to insert an identity. Because this rotation must be unitary, right? So what is a unitary matrix again? Do you remember the definition? Say again? Say again? Yes, U dagger it was. But actually, I'm going to insert the M. M is also unitary. So this is M dagger M. Okay. This means M dagger equal to U inverse, right? Because this is I. Because they are unitary. Okay. Because between all the transformation of this matrix, you can prove that they are unitary. So what is this? Look at this. This is M psi O. Maybe let me just summarize this one. M psi O. is what?
Sine nu.
Sine nu. Very good. Psi. Okay, so this is polarization. I call this psi, PSI. Okay, PHI, phi is this one. The rotator one is phi. Before rotation is psi. Right? Okay, and now you're saying that is it? No, this is nu, right? Because it's O times M, so it's nu, right? So this whole thing equals to, let me move this a little bit. M U O M dagger psi nu. Right? So here I have this U nu times psi nu equal this whole thing times psi nu. Then what does it mean? It means U nu must be equal to M times UO times M dagger. Okay, so let me annotate a little bit. I know you will have problem when you study this, right? The first thing is to understand their relationship, and then eventually come up with this equation, phi nu equal to M times phi O. And then I continue here. Right, and this is 4, this is 5, and this is 6. Now, this is such a derivation I hope you can appreciate. It's very confusing. I can tell you it's very confusing, right? But this involves two things. One is transformation of coordinate, which you use the M, right? You see the same vector in different coordinates. Then you use M to represent it. And then you also have the rotation of the vector. It can be, when you rotate it, you can see it in the old coordinate or in the new coordinate. And how does it represent the rotation in the new coordinate is related by M times UO M dagger. And you will find this useful later. Yeah. No, this is a matrix. It does not obey the commutative rule, right? So it has to be M here. Now, the way I memorize this is this. You see, if you transform a vector from an old basis to new basis, you multiply by M, right? How about for matrix? You just put the M in front and then M dagger after it. Then you can memorize. That's how I memorize it. Is that okay? Any questions? Okay. Assume you are okay and move forward, but you will find this useful in the future, okay? Another thing is about the trace, right? I don't know if you all remember what is trace, but let me remind you, you might find it useful. This time I'm not going to talk about entanglement entropy in this class because of time. But this is useful in the future when you are dealing with noise and other things. But so let's remind ourselves what is a trace, right? The trace of a matrix, if you have matrix, right? You just sum over the diagonal trace, right? We call it TR of the matrix. It's just the sum of the diagonal elements. This is definition. Okay, for example, my A equals to A00, A01, all the way to A0n minus 1, A10, A11, all the way to A1n minus 1, an minus 10, an minus 11, all the way to an minus 1, an minus 1. Then what is the trace? The sum of the diagonal element. And you see clearly it is trace of A equals to A00 plus A11 all the way to A, n minus 1, n minus 1. Is that okay? So you need to be familiar with the notation, summation of what? Can someone tell me? AII. I from where to where? 0 to n minus 1. That is the trace of a matrix. Okay? So let me give you some example, right? What is the trace of sigma C? Right? So what you need is to write down the sigma C, 1, 0, 0, negative 1. How do you calculate the trace? What is that? Can you give me the expression? 1 plus minus 1. Do you agree, everyone? That's the trace. We sum over the diagonal. Equals to 0. What's the trace of sigma x? What is sigma x? You should memorize it. 0, 1, 1, 0. What is the trace? 0 plus 0 equals to 0. What is the trace of sigma y? What is sigma y? 0 minus I, 0. So what is that? So here actually not very accurate. I should actually add a bracket because the matrix is there. But that's okay. 0 plus 0 equals 0. So it happened that the trace of all the poly matrix is 0. That's their characteristic. Okay? And then I need to tell you some basic equation that will be useful for you, right? So we already know that trace of A equal to summation AII means the ith element from I equals 0 to n minus 1. That's one equation. It turns out that trace of the multiplication of two matrices. Now you just say that we just say that they are not commute, right? A times B not always equal to B times A, right? But their traces are the same. Okay, we don't prove it, but this is very useful. Okay, now because of this, think about that. The trace of A in the new vector, in the new coordinate. Okay, we just proved that we can represent a matrix in any coordinate, right? Any new basis, right? I call it A new. How is it related to the AO, the O matrix, the matrix in the O coordinates? Remember? What is that? What is that? I just tell you how to memorize. M times AO times M dagger. Is that okay? But I just told you, inside the trace, they commute. Not because they commute, but the trace is the same when you commute them. So this is equal to what? M dagger AO. Right? Because trace AB equal trace BA. So treat this as A. Treat the whole thing as B. So AB equal to BA. You can rotate them, right? But what is M times M dagger? Identity, right? So what do you see? The trace is the same whether you look at the whatever coordinate, right? Which makes sense because remember trace very often represent the physical quantity if it is the eigenvalue. Remember when you represent a matrix in its eigenvector basis, the trace, the diagonal element are their eigenvalues. The trace is the sum of the eigenvalue. And if this is, for example, a Hamiltonian, which is the sum of the eigenenergies, energy, when you sum them together, they should be the same. It's just like the pencil. Maybe difficult to say, but I shall say whether I rotate their length is still the same. Not a very good explanation, but just a rotation, they are the same, right? So these quantities should be still the same, their eigenvalue energy, right? So their relationship. So that's why their trace needs to be the same. Okay, any questions? Yeah.
The pen is this way or this way, the energy is.
Yeah. Yeah. So that eigenvalue is a German, and eigen means the characteristic. You see, it has its meaning, right? Its characteristic doesn't change how you rotate it, how you transform it. In that sense, right? I'm not very rigorous, but I want you to appreciate that. So why the sum of the diagonal, the trace, is the sum of their eigenvalue. So now you think about the sum of the eigenvalue of sigma c, which is 1 and minus 1. If you go to sigma x, you actually do a rotation, then you have the eigenvalue. They have the same eigenvalue because they are same physical system. Whether your magnetic field is pointing in z direction, you measure the eigenvalue, or pointing in x direction, you measure the eigenvalue. The result should be the same, again, because the space is isotropic. Right, so they have this type of characteristic. Just have a feeling on that, right? I just a very hand-waving explanation. But again, eigen in German means characteristic. That is the characteristic of that matrix. No matter how you transform it, you still maintain the characteristic. Although you see that the matrix element change just crazy, right? Completely different. I rotate sigma c, do a transformation to sigma c basis, or sigma y, I even have the imaginary number. But the sum of their eigenvalue, or the trace of the matrix, still 0, does not change. Okay?